been asked to talk about bridges. I'm in the Civil and Environmental Engineering department, and bridges are, of course, part of structural engineering. And I teach a course in structural engineering that deals a lot with bridges and their history. And I'd like to talk about the importance of history to engineering today. I will talk about it in the context of bridges, but in fact, I believe that there's a lot broader application of these concepts. This was the Golden Gate Bridge proposal from about 1920. Now, what is it? It's not a familiar kind of bridge. In fact, it's what we'd call a hybrid. It was part suspension bridge and part cantilever. What is a cantilever? Well, it's basically a big bracket, and you can see that in this slide. The state of the art of bridge building, especially what's called long span bridge building in the 1920s, was that bridges spanned about 2,000 feet, but no more than that. If you wanted to build a bridge to cross the Golden Gate, you needed something 4,000 to 5,000 feet. So this engineer, his name was Joseph Strauss, put together one suspension bridge part and one cantilever bridge part. And I'd like to talk about the suspension bridge and the cantilever bridge to see why something like this could happen. As you know, the Golden Gate Bridge ended up looking quite different, and most people would say, thank God. Back in about 200 years ago, in the early 19th century, that's when the modern suspension bridge came to be. And what do we mean by modern? We mean using iron or steel in its chains or cables. A lot of these bridges suffered a lot of damage in the wind, and this is one example. This obviously gave bridges, suspension bridges in particular, a bad reputation. So a lot of engineers tried to avoid them. This was especially true in Britain. It wasn't until the 1960s that the British began to build suspension bridges. But it was different in the United States. One of the big challenges for us to build a suspension bridge that was considered successful was that it could carry railroad trains, and you can see that this one does that, and that it could stand up to storms, to heavy winds, hurricanes, and the like. Well, John Roebling, he was educated in Germany, came to the US in the 1830s. He found, by studying failures, and there were plenty of them reported in the press and in the literature of engineering and science, that if you wanted to stop bridges from collapsing in the wind, then you needed three things. One was weight. Now, as you know from physics, weight is related to mass, and mass is associated with inertia. So if the bridge has a lot of inertia, gusts of wind are not going to bother it very much. So weight was very important. The longer the bridge is, the more it weighs, so that works in your favor. Stiffness. You don't want the bridge to bend too much. This bridge that we see here has two levels, the top and the bottom. They were connected, not shown so well in this diagram, and that gave it stiffness. Finally, stays. Those diagonal lines you see are cable stays, or stay cables, and they kept the bridge from being tossed around in the wind. You know, when you're in an airplane and there's turbulence, you know what happens. The plane goes up and down erratically. Well, these cables were supposed to check that for the bridge. John Roebling went on to design the Brooklyn Bridge, one of the most famous bridges in the world. This was completed in 1883, and it today is still considered one of the masterpieces of bridge building. It connected what was then New York City, principally Manhattan, with what was a separate city, Brooklyn. But what happened in the meantime was that cantilever bridges became popular. In particular, one that was being built in the 1880s near Edinburgh, Scotland. This was an important bridge to complete the railroad link up the east coast of Scotland. Here you can see this bridge under construction. The distance between the towers is about 1,700 feet to give you a sense of scale. This is an enormous bridge. It had a span greater than the Brooklyn Bridge did, which is about 1,600 feet. And you can see how the bridge is being built without any scaffolding or support underneath. That was one of the big advantages of the cantilever bridge, the construction method. And that's where it derives its name from. Anything that sticks out and is supported only on one end is called a cantilever. So if I stick my arm out, that's a cantilever, effectively. It was so unusual at the time that the engineer, his name was Benjamin Baker, had to give a lecture to explain not only to his fellow engineers, but also to the public, how this bridge worked and why it would be safe. And that was very important because there had been some accidents on this railroad line, and if there was going to be a winning back of the confidence of the riders, potential riders, they'd have to understand what was going on. So this cantilever model, often called a human cantilever, became very, very famous. And the idea was that these two guys sitting on the chairs, they could feel the forces in their arms. They could feel them being pulled. And that gave an inherent sense of how the bridge was working. This is the completed bridge, the fourth bridge, completed in 1890, the first major bridge made all of steel in the world. It's still very much in use and very celebrated in Scotland. Other bridges began then to imitate it. Whenever there's a success in engineering that has great notice, other people want to emulate it. This was a cantilever bridge under construction in Canada, across the St. Lawrence River at Quebec. And you can see it's a cantilever because it's supported only at one end. And they were working on this bridge when it suddenly collapsed without warning, and it claimed the lives of about 75 construction workers. This always brings attention to the accident, and it became really the death of the cantilever bridge. But accidents do happen, and bridges are usually rebuilt. And on the left here, the bridge was rebuilt about 10 years after the collapse. A little modified design, and but not substantially different in its span, 1,800 feet. To this day, that's the longest cantilever bridge in the world. And this is one of the consequences of failure of a bridge, or of anything. Its technology suddenly becomes suspect, as it actually should. There are investigations, there are probings, but generally it's then the burden of the engineers who want to build a new cantilever to really establish its safety. But in the case of bridges, the suspension bridge was an alternative. Anything you wanted the cantilever to do, the suspension bridge could do. And so effectively, anything over about 1,500 feet wasn't going to be a cantilever, it was going to be a suspension bridge. To this day, the suspension bridge is the one that you use for longest distances. Well, let's get back to the Brooklyn Bridge and see how it evolved. The walkway of the Brooklyn Bridge is famous. It's considered one of the most really glorious pedestrian experiences in the world, to walk across the Brooklyn Bridge. Very thoughtfully, the engineer Roebling put the walkway high above the traffic, so that wasn't a problem. He also made it clearly wide enough so people were not crowded. And walking across the bridge gives you this great experience of walking into the cables, into the net that is so much an iconic aspect of the Brooklyn Bridge. Because the Brooklyn Bridge was so successful, not only architecturally, but also structurally, other bridge designs began to emulate it. But remember, John Roebling said, to be safe, to stand up to the wind, a bridge must have three qualities. It must be massive, have a lot of weight. It must be stiff, and it must have these diagonal cables that you see are part of the characteristics of the Brooklyn Bridge and other bridges that Roebling designed and built. So what happened? Well, as more and more bridges became necessary. And one of the reasons bridges become necessary is that the population grows, traffic grows. In the case of the Brooklyn Bridge, it brought so much traffic into Brooklyn that there was need for a new bridge within a couple of decades. And that new bridge was this one, the Williamsburg Bridge. About the same span as the Brooklyn Bridge, about 1,600 feet. But most people consider this an unattractive bridge. It's a very utilitarian bridge. It's all steel. It was relatively inexpensive to build and also relatively quick to build. But it has no real character. And if you look at it closely, you see something is beginning to change. It obviously is a very massive bridge because of this big truss. Whenever you have big diagonals and so forth, this is the truss component. That was necessary because this was going to carry New York City subways across the East River here. But if you look closely, you don't see any of those diagonals. These were considered redundant and unnecessary, even at this early stage after the completion of the Brooklyn Bridge. It was thought that this was like a belt and suspender system. Why do you need both? So they were just disregarded. The next bridge was the Manhattan Bridge, and because of the criticism of the Williamsburg Bridge as being so utilitarian, here you see there was an attempt to sculpt the towers. They are not just pieces of steel connected together, they're actually pieces of sculpture. This photo shows the difference between the Brooklyn Bridge in the foreground and its diagonal stays, and the Manhattan Bridge in the background with none of them. Just vertical cables coming down from the main cable to support the roadway beneath. So what's happening here, and this is a fairly general trend in engineering, I'm looking at it in a long perspective of bridges, but it happens in all sorts of technology, even current technologies. Changes are made that can have adverse consequences, as we'll see. Here's another bridge, 1926, the Benjamin Franklin. Same thing you see, no diagonals, heavy truss to keep it stiff. It's a very wide bridge, as you can see, so it has two of the elements, but not the third. But then something happened in the early 1930s, and that was this bridge, the George Washington Bridge. If you know Manhattan Island, the bridges I've talked about previously are all on the east side, across the East River. But there's also a western boundary to Manhattan Island, and that's the Hudson River. And the Hudson River is about twice as wide as the East River. So that's essentially why it wasn't bridged until about 4 or 5 decades after the East River. Now, this bridge is very interesting, and it set a new aesthetic for bridge building. Even in engineering, there are fads, fashions, aesthetic considerations. We look at this bridge. It's an all-steel structure. We notice it has none of the diagonal stay cables that Roebling thought were essential, but also it has no real stiffening structure. There's no truss to it. So this introduced a new change that was going to be incorporated into bridge building in the 1930s. And that was all you needed was a very heavy bridge. And that's what this is. It's very wide. If you know this bridge, it has about 7 or 8 lanes of traffic, and plus 2 wide sidewalks, one on each side. So any time you have a bridge that's wide, you necessarily have a bridge that's heavy. If you know this bridge, by the way, you say, well, it doesn't look like that today. No, because in the 1960s, 30 years after it was built, a second deck was added, which changed its appearance. But this is how it was built, designed in the 1920s and 30s, early 30s, and then other bridges wanted to copy this look. And this look basically meant that the roadway should look as slender as possible. It shouldn't be deep, it should be slender. Remember, Roebling really didn't promote that, he promoted just the opposite. So what happened? Well, bridges began to be built very light. The Golden Gate Bridge, this is of course quite different from the one I opened up with. The Golden Gate Bridge does have a truss, it does have stiffening, but very light. And in fact, shortly after the Golden Gate Bridge opened, it began to move considerably in the wind. The roadway would move, it would sometimes undulate, and that's because the truss was simply too light. It was fixed by adding additional steel, but that also adds weight to the bridge. That's good for stabilizing it, but it's bad if you want to have the bridge carry more traffic in the future. And in recent years, for example, they've wanted to expand the Bay Area rapid transit system across this bridge, but they can't because the bridge is carrying its capacity now. The Golden Gate Bridge is 4,200 feet between the towers. That made it the longest bridge of its kind in the world. Then what happened? All these bridges that I've been talking about are in metropolitan areas, San Francisco, Philadelphia, New York. But what happens if you start building bridges in remote areas, like upstate New York, going over into Canada? Well, there's not much traffic there, so you don't need 8 lanes of traffic, you need 2. And what does that mean? That means a very narrow bridge. What does that mean? That means a very light bridge. Well, the cables of the Roebling, the diagonal stay cables, have already been, dismissed as unnecessary. The truss, the stiffening, has been dismissed because the George Washington Bridge didn't have them. Now you've got a very light bridge, and what happens? When the wind blows in certain ways, the roadway of this bridge undulates. And this took engineers by surprise in the late 1930s. This is one example, the Thousand Islands Bridge. This is a bridge in Maine, the Deer Isle Bridge. The same thing, very narrow, very light, therefore. It also began to undulate, in some cases so badly that the bridge had to be closed. So if you go to this bridge today, you see it's all trussed up, it's wires going every which way, and this was to retrofit it, to deal with these problems. Another bridge is the Bronx Whitestone Bridge. Notice, all in 1939. That means all designed pretty much to the same state of the art. This bridge was deliberately designed to be an aesthetically pleasing bridge. You notice the anchorage in the foreground is sculpted, the minimalist arches and so forth. Well, this bridge also had its roadway misbehaving, if you will. When that started happening, they thought what they could do, and one of the things they did was they added this truss to the top of the bridge roadway, and you can see the diagonal cables were also added. In other words, they went back to something that had happened, in the previous century. Well, that sort of fixed the bridge, but I used to commute over this bridge, and in stop-and-go traffic, when you were stopped, you could feel the bridge heaving up and down very significantly. These bridges can be very flexible. Now, if you know this bridge today, this has been corrected with other technologies, but I won't get into that now. Then, of course, there was the Tacoma Narrows Bridge, which you may have heard about. This was completed in 1940 out in Washington State. Again, it was completed at a time when the area around Tacoma, Washington was not very well developed. That meant not very much traffic, therefore a requirement of only a couple of lanes on the bridge, very narrow sidewalks, and that made it a very light bridge. What distinguished this bridge from the others we've been talking about is that it was very, very long compared to the others. It was 2,800 feet between the towers. That made it the 3rd longest suspension bridge in the world at the time, behind the Golden Gate and the George Washington. Not only that, but it was also narrow. And what engineers are interested in is not absolute numbers so much as relative numbers. The ratio of the width to the length, for example. And when that's looked at, this was way outside the realm of experience. And you probably know the story that in November of 1940, it began to twist. Prior to that, it had just undulated like these other bridges. They had connected cables up to try to stop it, but some of those cables slipped out of position, and this was the result. It was captured on film, not very high quality, as you can see, but eventually it twisted itself apart. The concrete began to break up. That made it even less stiff, and that was the consequence. A real landmark failure. Fortunately, nobody was killed in this accident, So the suspension bridge survived in a way that it was considered something that could be fixed, the problems with it. There's always a report, there's always an investigation, and the lessons learned in the investigation of this was that, in very simple terms, wind is the enemy of suspension bridges. In other words, it was wind that did this. If there were no wind, that wouldn't have happened. Another observation was that flexible decks are vulnerable to the wind. Now, the reason these things are important, they might seem trivial, is they weren't taken into account in quite the way they needed to be when the bridge was designed. But 100 years earlier than this, in 1841, John Roebling actually published a paper where he talked about these same things. And that's how he reached his conclusion that a bridge should have weight, stiffness, and stays. So if you forget the past, something's going to happen that you don't want. The Tacoma Narrows Bridge was rebuilt just as the Quebec was. And what do we notice? Well, it suddenly has a very deep truss, something it didn't have in the original version. It's also wider, in part to gain weight, but also in part that just the talk of the bridge being built there made the population grow. So there was a need for more traffic. Today, if you go there, you'll see a second bridge beside it because traffic continued to grow, population continued to grow. In the 1950s, suspension bridges came back. There was a hiatus during the war, in part because engineers were trying to make sure they understood what happened to the Tacoma Narrows Bridge, but also because the war made it difficult to get steel to build something like a bridge, which was not absolutely necessary. After all, you can use ferries. This is the Mackinac Bridge between the upper and lower peninsulas of Michigan, and it obviously has a very, very deep truss. The longest suspension bridge today, measured by central span, is in Japan. The Hashikaikyo Bridge, you can see it has the deep truss. There was a lot of concern in designing this bridge that it not misbehave like the Tacoma Narrows, and we see it's still standing today. I'll close with this quotation, famous quotation: progress, far from consisting in change, depends on retentiveness. Those who cannot remember the past are condemned to repeat it. And I think we've seen that that's exactly what happened in the case of these bridges. So thank you very much for your attention, and I'd be happy to answer questions. Are there any questions?
I actually have a question.
Yes.
I've really admired the bridges of Calatrava. Can you talk about those? They look so strikingly different, and they're so sweeping. Are they ahead of their time, or still functional, or what do you think?
Well, Santiago Calatrava is a Spanish-born, Swiss-educated architect/engineer who creates what some people might call organic designs. They have very flowing lines. They don't have the rigid lines of a steel structure, for example. He works a lot in concrete. And he's worked on some bridges, some rather modest spans, pedestrian bridges, others a little larger, but nothing in this category here. He has a mixed reputation among engineers. Some engineers feel that he's more architect than engineer, which means that he places the appearance of his structures above the constructability of them. So some of his structures are very expensive to build for that reason, that he doesn't consider that so much. He was commissioned, for example, to build the concourse, I guess you'd call it, for the World Trade Center transit hub after the 2001 terrorist attacks. That still hasn't been completed, and it's had to be cut back considerably just to save money. Money is always an issue in these large projects. And a lot of what I've talked about, although I didn't emphasize it, was done for the purpose of saving money. Obviously, if you don't put these cables, these stake cables in, then you save money. It's cheaper. So it's a very tempting thing to do. And engineers don't work in isolation. They work very much with city planners. They work with budget people. who are usually the people that are usually considered the owners of the structure, because we're talking about millions and millions, and today going into billions of dollars for some of these really major bridges. Yes, sir?
I've seen highway bridges now that are single cable.
Yeah, I think I have a slide. You mean things like this? Yeah. Yeah. Now, what we see here, this is called a cable-stayed bridge. And here, you don't see the suspension cable from tower to tower. This is like taking that away and just leaving Roebling stay cables. So the roadway here is suspended directly by the cables from the towers. This has an advantage in construction, and that's one of the reasons it's becoming so popular. And this is one from Florida. This is the Sunshine Skyway bridge. Just as an aside, this bridge was built as a replacement for a cantilever bridge that was knocked down by a ship. So there's a lot of interaction among these different types. But this has become very popular, in part because it's very distinctive. Here the cables, for example, are painted yellow, or I guess they're in yellow plastic sleeves. The bridge can be constructed like a cantilever effectively, and it has those advantages plus the cost. Originally, these bridges were, they originated in Germany after the war. There were a lot of bridges bombed out, as you know, but the foundations remained. And the challenge was, could you build a lighter bridge on the old foundations, which would mean if you could carry heavier traffic on it, because you didn't have to have the bridge weight bearing down. So you could replace any bridge weight you saved with traffic weight. And they were meant to be relatively modest spans, up to about 1,200 feet. But today, these bridges are being built 2 and 3 times that length, which is a sure sign that you're getting into possibly unknown territory. One of the things about building large civil engineering structures like this is that you're going into untested territory. If you lay it out on paper, if you design it on a computer, it's all theory until you build it, until the wind takes hold of it. You don't control the wind. You can test in scale models in wind tunnels, but that's not the real thing. Civil engineering structures are unique in that regard. They present these additional challenges. I did have some extra slides, just that kind of question always comes up. This is one that's recently completed in France. This is a Millau viaduct over a deep valley, the Tarn Valley. And it's an extremely dramatic bridge. When the fog comes in, it looks even more dramatic. I don't think I have a Calatrava slide, but his bridges are, a lot of them are of this nature, but he does funny things. He tilts the towers, he uses fewer cables, and so forth. Any other questions? Well, I think that's about right on time, huh? Okay, well, thank you.